Our next speaker is Al Pisano, who's a distinguished professor at the Jacobs School of Engineering at, he's the dean, my bad. Probably a distinguished professor too, at the Jacobs School of Engineering at UC San Diego. Professor Pisano.
Well, great, Ed. Thank you very, very much. Let me share my screen, and I'd like to begin a presentation. Okay, please let me know if it looks good, and if it doesn't advance in a moment, just check with me. I'll make sure it works great. So first off, I want to thank everyone at the NAE for the opportunity to speak about the extraordinary engineering impacts on society that NSF investments have made. I have many friends at the NAE and the NSF. If you're out there, hey, hello. And I want to offer that I am pleased to have been a small part of it, but mostly what I'm going to do is speak about the incredible work of others. And I'd like to offer this theme. Sometimes the big NSF impacts come from the investments NSF makes behind the scenes that enable the impacts. And we've heard a little bit about that in the previous speaker's talk about Millie Dresselhaus, how Millie was able to make many other things happen. I'd like to talk about NSF investments that have had direct and secondary effects on society. So not many people may realize that the NSF has been supporting very large infrastructure projects, not just internet projects, not just communication or big science projects, but very large infrastructure projects for something that you might think is as mundane as a shaker table. And I can assure you there is nothing mundane about a very large-scale shaker table. And in fact, I'll offer some interesting thoughts about LH Post, which is the large, high-performance outdoor shaped table. So let me just get to the punchline right away, and then I'll show some of the interesting parts of how all this came together. Many people take earthquake safety for granted, but you have no idea how much in the way of computational models has to be developed in order to try to figure out how a building or a bridge or an overpass or a road might react to an earthquake. And worse, you can't stop at just a model. You've actually got to back that up with experiments. And even more important, the results of both of those have got to be driven through the building codes. This is a case where if you don't go all the way through to working with the state and the federal government and the local authorities to actually see changes in the design codes, then the wisdom of how to save people's lives in an economic and sustainable manner via better structural design just can't happen. And you can imagine there's plenty of research on new kinds of concrete and plenty of research on new kinds of fixtures, but the investments into the infrastructure that is used to test all that is essential. And if it's not done, you will not get the output you want, which is the saving of lives in a way that society can afford to implement. So let me tell you almost a 20-year story. So many, many years ago, around 2002, the faculty here envisioned a very large shaker table facility to be built near campus and used in an outdoor format to test buildings of literally unlimited height. There are many shaker tables inside a building. But you can imagine that you can't put a big model in there because if the model falls over, it damages the building. Or worse, if you build a model bigger than the building, nothing fits. So we're taking advantage of the fact that we could build a shaker table that could carry 400 tons and shake it as any earthquake has shook a building. And because there was a funding shortage some years ago, that table was designed to be a full 6 degree of freedom motion, linear in 3 directions, rotations in 3 directions, roll, pitch, yaw, but originally outfitted as a 1. And it's only very recently, it was awarded just 2 years ago, and we just had an opening ceremony. The table has been upgraded to full 6 degree of freedom. So the United States possesses the largest weight bearing, the largest height capacity 3D shaker table in the world. And that is one of our secret advantages to having the best earthquake standards on Earth. So we were very honored that the NSF director, Panch Panchanathan, came to the commissioning ceremony for the 6 degree of freedom system. And being a mechanical engineer myself, a personal note, I worked at General Motors, Singer sewing machines, and Xerox photocopiers. I was an engineer in the pen, as it were. I have a deep love of seeing science and engineering instantiated in physical things. And so I couldn't resist putting this video up. It only takes a few seconds. Whoops, sorry. All right, so what you saw there was a simulation of the Lola Prieta earthquake, one of the most destructive earthquakes in the United States. Imagine 400 tons on that table and all those rapid motions occurring despite that huge amount of weight and inertia. So there's an engineering story behind the engineering of earthquake safety, and it's how on earth do you engineer a huge, huge table that can shake huge, huge structures? And I won't go through all the details of it, except to say it is a huge endeavor. There is a huge building in which several electric pumps labor away, 400 horsepower each, pumping up the pressure in a huge set of reservoirs. And remember, the pumps may run for hours, but the earthquake simulations take just seconds. So 400 horsepower is the rate of one of the pumps. But if you release all of that energy 1,000 times faster, that's the equivalent of 400,000 horsepower at that moment. Huge piping and a bunch of engineering challenges to be able to enable us to use special hydraulic oil that does not absorb air, in order to push a set of servos around in order to implement all the motions to the building. Now, you would imagine, well, okay, earthquake safety is all about things like hospitals and stuff. No, you actually have to worry about parking structures and other artifacts, because if those buildings collapse, they cause damage to their environment. You would say, well, wait a minute, parking structures. No one likes to put a lot of money into parking structures. It's a tough business running a parking structure business. If I were to implement extremely burdensome earthquake codes, I could deleteriously impact the economy. Well, one of the special tricks that we do with earthquake testing is we work on what is the minimum reinforcing you need in order to make a building stand up. This reduces the weight of the building and increases its ability to withstand an earthquake. So let me show you what happens when you have a poorly designed structure. So what you see is that the structure is actually coming right off the foundation. This is a case where you have not correctly assumed the directions of the forces. The structure may have been stronger in a different direction, but we found the particular weak point of this structure, and as a result of this, there were building code changes made in order to improve earthquake safety. And the thing I'm pointing to is that big slab of concrete all the way at the right with NEES and EES written on it. That was supposed to be a stabilizing plate for the earthquake in that direction. You saw that it came right off the foundation, and therefore we stopped the test before the building fell over. If you take highway safety for granted, so I'll stop there and say that was a close-up of if you don't think of all the details about how to build a structure, you can leave a flaw. That flaw will cause a crack. The crack mitigates the ability of the stiffening structure, and the whole building fails. So we all know that a lot of engineering is about getting the details as well as the overall plan right. Earthquake testing is where any flaw that exists will come to the surface. Now, I won't go through an endless series of structural tests, but I do want to offer that if you've ever driven over a bridge, then you should be thinking about the ability of that bridge column to sustain damage, and I won't run the test here. If you've ever driven over a structure made of pylons, this is a structure that was used in the Takatori train station, and we're simulating the Kobe earthquake of 1995. Just by looking at the picture, you can see that that column did not do well. And you would say, I can't imagine why. It's filled with steel and excellent quality concrete. Well, it's all about the direction and the lay of all the materials. Let me point to an issue that I think global warming and climate change is going to drive. This is very recent research. So imagine a world in which tall wooden structures are feasible. Very tall wooden structures have some advantages. Concrete is a very carbon dioxide intensive industry. Not many people realize that 2.5% of the carbon dioxide released by humans comes from concrete plants. The carbon dioxide comes from the burning of the limestone in order to make the cement. What if you didn't have to burn all that limestone and make that cement? What could you replace it with? Well, for many structures, you have a naturally carbon sequestered material called wood. Carbon from the atmosphere, carbon dioxide is captured by trees and used to build the cellulose that we use, that we enjoy in the wood that we harvest from the trunks. Here's an example of large-scale wooden structures. This is a large-scale wooden structure that has a design flaw. These are always more interesting than the ones that don't have flaws. I'll just play a short video about that. All right, so that is a reconstruction of a typical building built in San Francisco. You'll notice all the red reinforcement structures we put up because we knew it was going to fall. We have since worked with the state of California to put together the retrofit rules so that without putting people out of business, without driving people broke, you can actually correctly retrofit the building in just the right way so that you don't get that catastrophic collapse. And those of you from the West Coast would recognize that as 3 levels of apartments built over a first floor, which is entirely garages. So you'd say, well, it looks like they didn't reinforce the first floor enough. And you're right. So let me wrap this up by saying there are a myriad of things that need to survive disasters. And I won't go into the combined disaster work that we do, wind and earthquake, earthquake and fire, fire and earthquake, et cetera, et cetera. But I just wanted to make a point. There is a lot of investment in infrastructure that no one pays attention to, and that infrastructure is what makes the engineering and science advancement go forward. So there's engineering within the engineering itself, and many of these things have direct impact on saving lives and making our society more resilient against disaster. So Ed, thank you very much. I appreciate the time.
Thank you very much for a wonderful talk and for great videos. I will express some disappointment that you didn't find the opportunity to shake up my dear friend, Chancellor Khosla, using your shaker table, but I guess we'll for another time.
Yeah,
I just have one...
That video was embargoed. That video was embargoed. I'll leave it at that.
All right. The question I have is, you personally have also been involved in MEMS research as well, and I'm curious, which also is about rigid structures and vibrating structures, and I'm wondering, is the big of earthquake and the little of MEMS, are there things that relate to each other in terms of the research and how you build resilient structures?
Yeah, so Ed, it's the answer is yes, indeed, and the meta wisdom, I'll call it, the size and time scale shift wisdom is certainly there. All the vibration modes, all the deflection modes you see in these large structures exist in microstructures. Except that you excite them differently and you measure them differently. And in fact, I'll offer this as a thought. Every electronic signal processing system runs all those electrical signals, every filter, every radio, everything, eventually runs that electrical signal through a mechanical structure, a SAW filter or some other structure similar to that. All filtering is done mechanically. So these vibration modes have analogs at the microscale, nanoscale, and I find it interesting to see that, yes, there are strong parallels between them, and there's a lot of wisdom that carries back and forth across the two.
Great. Well, thank you very much, and we look forward to you joining us a little bit later in the discussant section.